Hey guys, in this video we're going to talk about the fundamental theorem of calculus. To begin, we start out with some random function. X-axis, y-axis. Suppose our function y of x looks something like that. Y of x. And now what we're going to introduce is something that I'm going to call the area function. The area function. So the area function is going to be pretty much what it sounds like, the area under the function y of x, so the area between the function y of x and the x-axis from the point 0 to x. So it's going to be this red area right here. So that red area we're going to call a of x. Now I started at 0, but actually to do what we're about to do, it doesn't matter where you start, as you'll find out. Because what we're going to do is we're going to go ahead and differentiate this a of x function. And as we know by now, differentiation only cares about a small neighborhood of the point we're differentiating it at. So we're going to differentiate a of x. So to begin, well, we know that a prime of x, the derivative of a of x, that has to be equal to the limit as h gets closer and closer to 0 of a of x plus h minus a of x, and that whole thing is divided by h. So that's the limit we've got to work out if we want to differentiate this area function. Well, let's suppose h is bigger than 0 for now, but the same kind of thing works if h is smaller than 0. So if h is bigger than 0, let's go ahead and make this one here the point x plus h. So here is the point x plus h. Okay, so that means that this distance here from x to x plus h has to be h, because it's x plus h minus x, which is h. Okay, so also, what I want to do is actually make a couple of rectangles out of this thing. So the first rectangle we're going to make is this big one up the top. What is the height of this rectangle? So I'll draw another line there. What is the height of this rectangle? Well, the height of this rectangle has to be y of x plus h, because it intercepts it has a corner at the y of x function, and the input is x plus h. So the height of this rectangle has to be y of x plus h. We're also going to make another rectangle, starting at this point here. So this rectangle right here, this green rectangle. What is the height of this green rectangle? Well, the height of this green rectangle has to be y of x, because again, it intercepts the y function and it has input x. So the height of this green rectangle is just y of x. Okay, and now I'm going to shade some stuff in. Make this part blue. Make this part pink. Oops. Alright, now we're ready to go. Okay, so let's go back to our limit and see what we're trying to work out again. So the first thing we're trying to calculate is a of x plus h minus a of x. So let's go and have a look at that. What is a of x plus h minus a of x? Well, a of x plus h itself would be the area under the curve y of x, starting at 0 and going all the way to x plus h. So this would be a of x plus h. If I were to shade the whole thing in, a of x plus h would look pretty much like that. Now we're taking away a of x, which was the red part, don't forget. We're taking away a of x, which was the red part. And so all we're going to be left with is this little section right here. So that part that I just shaded in, that would be a of x plus h minus a of x. And we can see clearly that a of x plus h minus a of x is the green area plus the pink area. So let me write this down. Green plus pink is equal to a of x plus h minus a of x. Okay, great. Well, now I want to work out these rectangles. I want to work out the area of the green rectangle first. So, the green rectangle has an area of, well, the area has to be base times height, so it has to be the width of the rectangle times the height of the rectangle. Well, the width is x plus h minus x, which is just h, and the height of the rectangle, as we worked out before, has to be y of x. So the green area is h times y of x. Green area is h times y of x. Now I want to work out the area of the bigger rectangle. So this rectangle that I'm now covering in red around the border. So that rectangle has the same width. The width is still h, but the height is now y of x plus h. The height is this one here. So, and of course that rectangle is made up of the green, the pink, and the blue areas. So, that means that green plus pink plus blue equals, so the area of the green part plus the pink part plus the blue part has to be h times y of x plus h. H times y of x plus h. Why on earth are we doing this? Well, now we've kind of seen something pretty interesting. Because remember, a of x plus h minus a of x is actually the green area plus the pink area. And we have that the green area is h times y of x, and the green plus the pink plus the blue is h times y of x plus h. And we know that all these areas are positive, and so what that means is green must be less than green plus pink, which must be less than green plus pink plus blue. Let me write that down. So we can see from the diagram, because all these areas are positive, that green by itself, the green area, must be less than the green area plus the pink area, which must be less than the green area plus the pink area plus the blue area, because all these areas are positive. Well, we know that the green area is equal to h times y of x. The green area is equal to h times y of x. The green plus pink area is equal to a of x plus h minus a of x. And the green plus the pink plus the blue area is equal to h times y of x plus h. In other words, what this equation, this inequality at the bottom is saying is that h times y of x, the green area, is less than a of x plus h minus a of x, the green plus pink area, which is less than h times y of x plus h, which is the green area plus the pink area plus the blue area. Let's go ahead and write that down. So what we have what we have is that h times y of x, and this is for any h bigger than 0. This is for any h bigger than 0. H times y of x is less than a of x plus h minus a of x, which is less than h times y of x plus h. And now we're getting somewhere because we can just divide through by h, since h is bigger than 0. If h was smaller than 0, we could pretty much do the same thing, but we would be swapping the signs around. But the same kind of thing would work. So let's go ahead and divide through by h. And these h's cancel, and these h's cancel. And what we are left with is this beautiful statement. Y of x is less than a of x plus h. Gotta leave some space. A of x plus h minus a of x divided by h, which is less than y of x plus h. And this is true. This is true for all h bigger than 0. This is true for all h bigger than 0. What we're trying to calculate, though, what we're actually trying to calculate is the limit as h gets closer and closer to 0. What happens to this thing in the middle? What happens to a of x plus h minus a of x divided by h? Well, since this is true for all h bigger than 0, we can just let h get smaller and smaller for each of them. And now what happens? Well, this one here, the limit as h tends to 0 of y of x is actually just equal to y of x. Because as h gets closer and closer to 0, y of x gets closer and closer to y of x. It just stays the same. It doesn't change at all. Okay, well, this thing in the middle is actually a prime of x. By the way, because we're taking a limit, this is no longer necessarily a strict inequality. It can actually be less than or equal to now, because even though it's strictly less for all h bigger than 0, that doesn't say anything about what happens that doesn't actually quite say anything about the number itself, when the limit itself. So actually, this can be a less than or equal to now. And similarly, the limit as h tends to 0 of y of x plus h, well, that one's going to get closer and closer to y of x. If we go back to our diagram, as h gets smaller and smaller, as we get closer and closer to x, clearly y of x, the function y is getting closer and closer to y of x as our input variable gets closer and closer to x itself. And so this limit here is actually also y of x. And therefore what we have is y of x is less than or equal to a prime of x, which is less than or equal to y of x. And therefore what we've just worked out is that a prime of x is equal to y of x. So when you have a function like this, when you have a function y of x and you have the area function, which is the function of the area under y, between y and the x-axis, then when you differentiate that area function, it's actually equal to the function y itself. So a prime of x, a of x differentiates to y of x. So that's really interesting. And then maybe you were wondering why we spent that time doing antiderivatives. Well, the reason is because now this tells us that in fact the antiderivative of y of x with respect to x is actually equal to the area function plus some constant. So to find the area function of the function little y of x, all you need to do is take the antiderivative of it, because the area function is the function that differentiates to give us y of x in the first place. This constant c, what does that represent here? Well, actually, remember when I said it doesn't matter where you start from? Remember when I said it doesn't matter where you start from when you're doing these calculations? I started from 0, but I also could have started from this arbitrary point A. Notice that if I start from this arbitrary point little a though, this area here between 0 and A is some constant c. So it doesn't matter where you start from because the constant c is captured when you take the antiderivative. Because when you take the antiderivative, you're looking for all of the functions that differentiate to give little y of x. And so that's why you're adding that arbitrary constant on to take into account where did the area function actually start from. Okay, that's all for this video. Thanks very much for watching. Don't forget to check out the notes on the fundamental theorem of calculus and have a go at the exercises at the back. Take care. Bye.